Chris Mattson is going to start us off today. Chris is joining us as an assistant professor in the Department of Mechanical Engineering and is a director of the Design Exploration Research Group at Brigham Young University. Chris has an excellent background. He has a career award, a PCASE award, and just finished a Fulbright fellowship, and brings us to talk to us today about his work in providing clean water to over 100,000 people in Africa, East Asia, and a couple other continents around the world.
The story that I want to tell you today about the village drill is a story that represents the work of a lot of people. And the leader of that work is a fellow named John Renard. He's the president of wholives.org. I was fortunate to be a part of the project. He asked me to oversee the design and engineering of the village drill. The village drill is fundamentally about access to clean groundwater. And to get access to clean groundwater, there's 5 things that need to be done from a technical point of view. And here are those 5 things that need to be done. Now, wholives.org needed to succeed at all of these 5 things, but the village drill is just about one part of this. And it's about drilling a hole into the earth to access that water. So there's lots of ways that exist now for drilling holes into the earth, and probably the most popular way is to use a professional style drilling rig such as this one. Now there's lots of benefits that come from a system like this. There's also some drawbacks, and the biggest drawbacks here are the cost, the ability to access remote locations, and the amount of skill needed to run a machine like this. And so wholives.org approached us at BYU and asked if we would design an inexpensive alternative to this. And that's what we did. And this is the system that we created. This is called the village drill. It's a simple machine that can put a 6-inch borehole 250 feet into the earth. Now this system was designed by a group of 6 of my students. And here are the 6 students who worked on this project. And these students worked for 8 months on the project. And this is a picture of them with the second to last prototype that they had for the system. Now I want to split my time into 2 basic pieces. The first thing I want to do is just talk about how the village drill works, and then I want to talk about the impact of the village drill. So on to how the village drill works. First of all, the village drill accepts as input human power to spin this yellow wheel. And as that yellow wheel is spinning, this vertical yellow bar twists and transmits torque to the cutting bit, which is down here at the bottom of the screen. Now this vertical piece is called the Kelly bar. And the Kelly bar has the unique property of having a square cross-section, which allows it to simultaneously turn and drop while the bit is digging deeper and deeper into the earth. Now, a fundamental part of this system is this winch that's on this side here. And what this winch does is it controls the descent of the pipe as it goes into the earth. And if you don't have that, what happens is that the drill pipe acts like a gigantic nail that pushes itself right into the ground, and you can't spin the wheel any longer. So this winch is an essential part of this. And here's a simple video of the system working. And I'm showing you this so you can see how simple it is. You can see the winch working in the background. This video would be 2 minutes if I didn't speed it up. But you can see the Kelly bar descending. Now when the Kelly bar gets to this bottommost position, you unattach it from the drill pipe that's going into the ground, and you lift the Kelly bar up to the top and put in a new pipe segment, and you go and you do that again and again and again until you reach the water. And at the time that you reach the water, it's time to pull all the drill string out. And to pull the drill string out, what you do is that this middle section of the village drill simply comes off, and the drill pipe is pulled up 2 segments at a time. Now, to keep the pipe from falling back into the hole during that process, there's a slip plate that goes underneath the coupler that connects the pipes and holds it up while the winch cable is taken off and the pipes are removed, and then the winch cable is attached back to those new set of pipes that are still in the ground. Okay, the village drill is designed to dig down 76 meters. The deepest hole we've ever drilled was 73 meters in Zambia, but there's no indication that it wouldn't work to go to the designed amount of 76 meters. Now at the far end, down deep into the earth, the chips are removed as a cutting fluid. A mixture of commercial grade bentonite and water is pumped down the pipe and pulls the chips back up in the annulus created right there. All right, so that's the basic functionality of the village drill. And as simple as the machine is, I can assure you that each of its features were designed thinking about the users and thinking about the people who would need to deal with the village drill every day. So for example, this yellow wheel seems to be hovering in the air with no structure underneath it, and that was on purpose because so much work has to happen underneath that wheel. All the pipe changes are happening, and so we wanted to have nice, clean access. Another key feature of the system is that it comes apart into these strategically chosen pieces, which are very easy to assemble and very easy to transport, and allows the system to get into remote places where regular professional style drilling rigs cannot reach. So that's the basic kind of functionality of the village drill, and I think it's worth taking just a moment to ask ourselves, did the village drill team do what they were supposed to do? Were they able to create an inexpensive alternative to this system? And for all accounts, I can tell you that yes, in many ways, the village drill is less expensive, more transportable, and more approachable than this system that you see on the left. And what I mean by approachable is that when people see the village drill working in a village, they end up saying, I can be a part of that. I can participate. You don't get that same kind of sentiment about this. That's kind of like, I can't participate. I can't contribute to this. All right, well, that's meeting the design goal, but what kind of impact has the drill had? That's what I want to talk about right now is what kind of impact it's had. Now, I can tell you that we designed the drill 6 years ago, and we put the drill into service 5 years ago. Okay, and we started producing these drills. And we were patient, and we waited for 5 years to see what would the result of this village drill be. And I can tell you that I'll give you a tiny kind of summary of that data in just a moment, but I will invite you to go to my website, design.byu.edu, and download the village drill case study paper. And in the village drill case study paper, we've presented all the equations for the primary impact measures, the secondary impact measures, the productivity measures. These include things like jobs created and number of boreholes currently working and all of that kind of stuff. It also includes these time series plots where you see the entire history of the drill and the data that was collected over the last 5 years. And as an important part of that study, you'll find a full timeline of the project where not only the development dates are shown, but also all the 17 field trips that were needed and the introduction of the drill to all of these different places. That's provided in the technical paper. But let me just highlight a few of the key outcomes right now, and I'll point to the ones that have a black dot as being probably most interesting for you to look at right now, and I'll just highlight the one at the bottom for a moment. The one at the bottom describes people months of water, 4 million people months of water. And what does that mean? That means that if I have access to water each day during a month, I'm going to call that 1 people month of water. And if I go for an entire year, that's 12 people months of water. And if 100 people go to that same well, that's 1,200 people months of water. And the village drill has resulted in just over 4 million people months of water. Now, it's really important when we do analyses like this that we be very careful, because it's very easy to get it all wrong. And let me just say how important it is that we have a cautious analysis when we do this. So for example, if I were to look at the number of people that have been served by the village drill, now Nathan at the very beginning said that 100,000 people have been served, and that's the number I feel most comfortable with. I feel 97% confident in that number. But I could use numbers and come up with the estimate that 7 million people are being helped by the village drill. But I'll just tell you that would be wrong and that would be inappropriate. So I could show you the numbers that would lead to that. Now, we can look at this middle one. This middle one's better because it's more realistic. What it does is it says not all drills are always operating, and they're not operating as efficiently as they could, and not all holes lead to water, and not all pumps put into that whole stay functional. Okay? And once you take into account all of those numbers, you get realistic estimates, and these are more realistic. And once we run the statistics on the number, we can get pretty good estimates of where we are. Now again, in the paper that you can download, the full description of the uncertainty analysis and the Monte Carlo simulation that we did is described, and the results are presented there. Now at the very beginning, I mentioned that this is the work of a bunch of people. And I just want to highlight a few of those people. This is the Kenyan manufacturing team that has produced about 90% of the drills that are in service now. Okay, these are some of the well drilling teams that have gone out and put holes in lots of places. These represent just a few of the many NGOs who have bought the village drill and are using them to put them to work to help people get water. And these represent only just 20 of the 800 drill sites around the world where the village drill has been gone into effect. So I just want to end with one thing here, just the last few seconds, one final comment. And this comment is really about us and about this symposium and about engineering for global development and the essential question as to whether it's worth the effort, whether it's worth the time, and whether we should invest in trying to do this kind of work. And I'll just say that for me, the answer is yes. Yes, we need to do this. And this is even more clear when you look at the astounding fact that for every hour of engineering spent by this team, it resulted in over 1,000 months, 1,000 people months of water. That's 88 years of water. And if you ask me, I am more than willing to dedicate a portion or all of my career to something that affects people over their entire lifetime. Thank you.
Personally for me, I'm involved for a handful of different reasons, and one of the reasons is that there is so much that is unknown about how to succeed in this space of engineering-based international development. I mean, there's just so much that's unknown. And to me, that's very interesting. It means that there are research questions we can pursue. It means there's new findings that are to be had. And to me, I find that to be really exciting. Around 5 years ago, I was asked to go to Peru, to this town called Chiclayo, and to give a talk in Chiclayo. And one of the things they wanted me to give, they told me what the title of my talk was going to be, and they said that the title of the talk needs to be Social Injustice. And I thought that that was a little odd, and I'd already worked kind of in this area, and I thought that was a little odd. But then I gave the talk, and I thought about it for a couple of years after that, and it really rang true with me that there is a social injustice, that there is all this engineering effort that goes into bettering the world, but it's bettering the world that we're familiar with and not bettering the world that most of the population lives in. And so for me, I have this sense of, I have this interest in engineering, this interest in design, this interest in product development, and if I can't put it to work to make someone else's life a little bit better, then I'm not really quite sure what I'm supposed to be doing with that interest and with that skill.